All right, if you haven't already turned in the quiz, just make sure I have it before I walk out. As always, you can turn that in either on paper or online. If you haven't noticed, I did grade the test. Grades are in Canvas, but I have a couple people who need to make it up, so I'm going to hang on to the test until everyone's in. In the meantime, if anybody has any questions about how they did, or if they want to take a look at their test, we can do that. Just send me an email or come talk to me after class. Let me know when you're available to meet one-on-one. We can do that. Any other questions about anything before we continue? About the test, about what we've been covering, anything else? All right, let's go ahead and get into it. So we're in section 5 of chapter 2. This is about how it works and when to use it. So this function here, the quantity 3x plus 4 all squared. Can you do power rule? I mean, power rule is what I eventually apply, but what do I have to do first before I get there? Go ahead. Not factor, but expand. So yeah, if I factor, or if I I did it. If I expand this out, I get 9x squared plus 2 times 4 times 3x is plus 16. So expanding it out gives me this, and I take the derivative of that. What would that be? 18x plus 24. Any questions here? All right. So similar example, what if I have 3x plus 4, that quantity raised to the 12th power? But I find that derivative. So yeah, I mean, it would definitely take you a while, right? But based on the things you've done in here, based on the tools I've given you, you could absolutely do that. We're not going to do that using the things we have at our disposal now. So that's where the chain rule comes in. So in many cases, you can think of a function as positive sum of using the chain rule. Was it 3x plus 4? Remind me. 3x plus 4 to the power of 12. So what you're probably seeing here is you see a function, 3x plus 4. Previous power 12. So taking advantage of that relationship, I have a much more efficient, streamlined way to find that derivative. So if I have capital F of x, which is equal to f composed of g, I can find the derivative of this thing all at once by, and I'll explain that this will hopefully be a little more easy to see kind of systematically how this works. I'm going to do some examples. But I'm going to take the derivative of that outermost function, given that its input is whatever the inner function is. Then I'm going to multiply that by the derivative of that inside function. So in the case of this example, just kind of looking forward, what is the outermost function in this case? In the case of the f from the previous example. Maybe we should pause on that. I'll give you a chance to write. I'll give you another one. Maybe I should make it really clear that there's a multiplication going on somewhere here. All right, so let's take a look at this thing in more detail. And in order to really show how this chain rule works and make sure we're doing things in the right way, let's kind of model what this function does. So this function f of x equals 3x plus 4, that quantity to 12th power. Let's model this function as kind of as a sequence of instructions. What's the first thing that happens to x in this function? Like if you were to calculate this, what's the first thing you would do if I gave you a value of x? Multiply by 3, right? After that, what would you do? I would add 4 to it. And then what? Right, so raise it to the power of 12. And then that's it. So basically this is like your, instructions for taking x and turning it into f of x. So if I wanted to, I could treat each one of these 3 blocks as its own function. Would it be okay with you all if I just collected these together? So now let's do this. Let's just treat each one of these things as, let's call this guy g of x, and let's call these first 2 steps h of x. So the question I asked just a bit ago is, what is the outermost function? Now that I've kind of written out this block diagram, what I can ask is, what's the last thing that happens to my input en route to that input becoming f of x? What's that last step in this process? Yeah, raising it to the power of 12. So I'm going to call g of x x to the 12th. Basically, whatever comes into that block is going to get raised to the power of 12. By that logic, how can I represent this function h of x? 3x plus 4. Based on that, can we say this? F of x is equal to g of h of x. We okay with this so far? Right. So basically the way the chain rule works is this. If I want to find the derivative of my, this entire function, then basically I can kind of handle it in layers of this composition. So first thing I'm going to do is handle the outermost layer. So the outermost layer is x to the 12th. What is the derivative of x to the 12th? 12x to the 11, right? So it's going to be 12 times something to the 11th power. So I do need what g prime is, but remember, we've got to think about what the input is to g prime. In this case, the input to g, and if I look at my block diagram, the input to g is my x. Basically, it's one of the later steps in this function. So instead of putting x in this bracket, I'm going to put 3x plus 4. So basically, when I'm taking the derivative of some composite function, you got to treat all the so since I'm in a room with a lot of engineering majors, have you used the term in cascade in your engineering classes yet? And I'll just disregard that. Basically, you just have this sequence of instructions. That's the sequence of smaller. So basically what I'm doing is complicated function, I'm breaking them down into these nested simpler functions. So I've taken the derivative of that outermost function, respecting the fact that the inner function is the input to it. But now I need to multiply that by the derivative of the inner function. What's the derivative of the inner function going to be? 3. So simplifying it, 36 times 3x plus 4 to the power of 11. Go ahead. Right. So basically, so we're treating this as treating as a composite function. So yeah, basically we have kind of, we can handle it in smaller pieces, but we have to, treat each function as a discrete thing. And what I mean by that is that's going to be fine. Basically just keep differentiating all the way down until you get to the breakdown. The biggest breakdown I can do with so that's not quite true. So let me make myself some more room here. What if I said, what did I call the outermost one? So the outermost one is still x to the 12th, right? Then I asked you if I could combine those first two blocks. Let's say I didn't want to do that. Then I would say this is x plus 4, right? And then let's call the last one j of x. That one's 3x. So now that I have these three functions, the chain rule, I don't need to have two functions for the chain rule. I can have 12 and just work all the way down. So let's do this. This derivative is going to be g prime of what then instead? So h of something, right? But not of x. H of j of x, because now I've broken this function into three functions nested inside one another. So that's the first part of the chain rule. What would the next derivative look like? H prime of whatever its input is, which we've said is j. And then what's the next part of this derivative look like? J prime. And that's as deep as that's the whole nesting process, right? So now let's actually evaluate these things. We said that g prime is 12 times something to the 11th. In this case, what's that something? H of j, okay? H is x plus 4. That means h of j would be 3x plus 4. So it still looks about the same, right? All right, next piece. What is h prime? So what's h prime? 1. So then what's h prime of j? So there's no variable left there. All right, then the last piece is j prime of x, which is 3. So yeah, you can break it down to these. Looking forward, then you can break these down as into as small of these grains as you want, and as long as you're handling it properly, you're going to wind up in the correct place. Okay. Next, y equals sine of x squared. Let's do the block diagram thing at least one more time. So what's the first thing that happens to x in this function? It gets squared. What happens after that? We take the sine of it. Anything else? Nope. So that's now we have kind of a two-step process for how does this function turn x? So if I want to take the derivative of this function, I need to handle it in kind of the same way. And just to have names, let's call this guy g, and let's call this function h. So if I want to find dy dx, what derivative do I need to handle first? So I need to handle g prime. So I'll take that derivative. But what is the input to that function g? H of x in this case. So there's one derivative. And I need to multiply that by what other thing? H prime of x. So before we actually fill in the function specific things, one thing I want to highlight here is that, you know, chain rule is always going to kind of work in the same way. You're starting at the kind of the uppermost, quote unquote, outermost layer and differentiating back to whatever the input is, in this case, x. So I guess we should probably fill in these things. What are the functions g and h? We'll start with h because that's a little simpler. What's the function h of x? X squared. What's the function g of x? Why is it not sine of x squared? Right. So I mean, if you just look at if you just think about that smaller individual piece g, all that it does is take the sine of whatever comes into it. All right. So I think we're now ready to differentiate this thing. What is g prime of h of x? Cosine of x squared. And what is h prime of x? Just because I think this should be written the other way, I'll rewrite it once. That's a good derivative for that function. I'll stop here while you think of things to ask me. How are we doing with this so far? You are? That's good. All right. Looks very similar, but different. We want to do the block diagram thing one more time, or should we try to take those training wheels off? Okay. So I want to take the derivative of this. What do I need to think about? How do you want to start this? So you're saying g of x is equal to sine squared of x? I mean, if you just saw it, if you wanted to say that y was equal to g of x, you could say that, but I think we need to try to g of x is x squared. In your eyes, is g of x the outer? So we're gonna have a two-step function again, two nested functions. In your eyes, is g of x the outermost or the innermost of those functions? The outermost, right? So really, the difference here, I mean, we still have one of these two composed functions is x squared, the other one is sine of x. What's the big difference between the last example and this one? Right, so now I'm nesting them in a different order. So to really drive that home, I'll say this: y is equal to g of h of x. The first thing that happens to x is I take the sine of it. The next thing that happens to that is I square that value. So having laid out all those pieces, what's this derivative going to look like? So what's that outermost term going to become when I take the derivative? Just 2? Is it really 2x though? So I'll put it in parentheses here. Yes, the derivative of, and I'll make some relationships here, g prime is equal to 2x. And while we're at it, what is h prime of x going to be? Cosine of x. So yeah, the derivative is 2x, but remember, the input to g is sine of x. And then what's the rest of this derivative going to look like? Times cosine x. Any questions there? All right, so I'll back off a little more here. So how would you like to start this one? Is it possible to just do this all at once? If the answer in your head is no, that's fine. I'm trying to gauge where we are. How many different functions would be a good idea for me to treat this as? I got to vote for 2. I got to vote for 2 or 3. Both are possible. Let's try 2. So let's say that y is equal to g of h of x. So if I'm saying that that is the case, then we should probably talk about what g and h are. What is g of x? We got to vote for x cubed minus 1 for g of x. What would that make h? X to the 100th. We okay with that? I don't think that fits with the way that I broke it down to be. Yeah, so I mean, I gotta change one of these. That one seems more efficient. But yeah, I mean, so something to highlight there. It's important if you're gonna break this down into 2 functions or 3. Only important to also. Go ahead. It'll be fine. And I have to name a function anything. All right, so now that I think we have we've defined this well, so how can we handle the derivative now? What is y prime? $100 times x cubed minus 1 to the 99th power. Times what? 3x squared. But yeah, right here we have, this to me looks like h prime of g of x. And this to me looks like e prime of x. Take one attempt to simplify this, get 300x squared times x cubed minus 1 to the 99th. Any questions on this one? All right. I'll take my cues from you. I'll have to restart this thing. Okay. I got to vote for 3 functions. So, is that a question? Yeah. So that might be a good place to start. Yeah, if there's a way you can rewrite this, the power, what would the exponent be? Negative 1/3. Yeah, the cube, yeah, 1 over the cube root is the same as to the power of negative 1/3. All right, so we have a rewrite here. Does that change the number of functions we would like to consider this composed together? Okay, I'm gonna vote for 2 now. We okay with just treating this as 2 functions? Cool. So let's say f of x is equal to w of z of x. Just because I can call them whatever I want. If I call them that, what is w of x? Yep, this here, which means z of x is equal to. There we go. Then if I want to find the derivative of w of z of x, I get what? Maybe because we have a weird exponent here or a non-integer exponent, we should do some scratch work over here. What is w prime of x? Yeah, I heard somebody say this, but it sounded more like a question than an answer. We agree with this? Okay. Good. So, and just one thing to, at this stage, I'm willing to bet that somebody in their head thought negative 1/3 x to the power of 2/3 or something. Sometimes, especially when you have non-integer exponents or sometimes when they're just negative, it's tempting to add one when you should be subtracting one. So that's valuable to have, that w prime of x. Does that give us any help in constructing this larger derivative? How does it start? Okay. Believe that's what you told me. We agree with that. Okay. Looks good. And then what's the rest of this going to look like? Times 2x plus 1. If only if I asked you, or if what work asked you. But for the purposes of what we're doing now, that's I'm focusing on the actual derivative of it. So just to kind of recap, I mean, the first thing we did, and this might be a good idea to always look for that this at first, is can we re-express it to maybe think about it differently? Because I think I had multiple people who were tempted to think about this as three functions before this like redesignation here. Anything else about this one? But this thing. Should we expand the numerator denominator? Not to that power, right? So how do we want to break this one down? Okay, I got to vote for three functions. Go ahead. What's that? Okay, so I got to vote for three functions. I got to vote for two. One of those things is going to involve the quotient rule. Let's try that. So we'll call it h of k of t. Just curious, whoever said that we could do this three functions, what would the three functions be? Because here's one thing that I wanted to point out. If I break my three functions down into this, t to the ninth, t minus 2, and 2t minus 1, is there a way to nest all three of those, so compose those to make this function g? Right, so that's one thing to look out for. Sometimes the relationship you're looking at is not composition. Like in this case, I have the function j divided by the function k, which is a relationship between them, but is not composition. Composition is a very specific thing. So sometimes I think it's a good idea to, once you break this down in your head, make sure that what you've done is correct. Because for example, if you treated this as j composed with k, or vice versa, you would not wind up in the right place. So in this case, then, if we use h and k, h composed with k, what does that mean we're saying h of t and k of t are? Okay, so basically the inside of the bracket, which means h of t is just what? T to the ninth. So yeah, this set of parentheses is a rational function raised to the ninth power. All right. What is h prime of t then? T to the eighth. That's the pretty simple one. What is k prime of t then? How'd you get that? Okay, so let's break that down just because we haven't talked about that since Monday. How's the quotient going to start? So derivative of the first function of the numerator times the function in the denominator minus the first function times the derivative of the second all over t, 2t plus 1 squared. You said the numerator comes out to just 5? Go ahead and pause there. So any questions on where we got these different components? We got the two functions, we got their two derivatives, kind of irrespective of each other. But then having done all of that, how do I get g prime of t? We okay with that beginning? Yeah, I don't think I'm okay with that. So, and I'm really glad this came up because this is something we need to watch out for. So remember, when we take the derivative of composed functions, what is the input to the function g? Or sorry, to the function h, I guess in this case. The input to the function h is not k prime, just k, right? So what's inside this bracket should be t minus 2 over 2t plus 1. Are we okay with that beginning? Good. All right, then what is the rest of it? Yep, then it's times 5 over 2t plus 1 squared. We're just trying to simplify a little bit. Equals 45 times t minus 2 to the 8th over 2t plus 1 to the 10th. Lots of ways to make that look. Any questions here? Okay. How would we deal with this? It's kind of strange. Any thoughts popping up on how we would? Go ahead. When you say each one, what are you referring to? Okay. So I'm hearing one breakdown like this: y equals g of x, not composed, but just that product, right? Four functions, and how are they related? Man, we could do four functions, but it's really important to know, like, are they all composed with one another? So we got this definition here, y equals g of x times h of x. If we go with that, then what am I saying the g of x and h of x are? Okay. So are we okay with that so far? We might keep kind of trying to drill this down, but are we okay with that so far? Okay, if we're okay with that, should we stop there, or should we try to make some simpler functions for ourselves? I could do what? Okay, so I could say g of x is equal to, so if I'm going to break this out, let me ask this way, let's be specific. If I break g down, am I breaking it down into things that are composed, added, subtracted? Like what's the relationship? Well, I'm not even ready to do any derivatives yet. Like I'm just breaking down. So it sounds like we wanted to break down g into something simpler and h into something simpler. So what I'm asking is, if we're going to break down g of x into smaller functions, how in your mind are those functions related to each other? Okay, so that's what I was getting at. So we're saying composition. Same for h? Yeah. Then I guess it makes sense for us to figure out what all these things are. Okay, so now we have this thing in 4 functions, right? So y equals g times h, which is the same thing as a of b times c of d. You want to go any further, or can we start doing the derivative now? Before we do, I just want to stop though. Are we okay with where we ended up? I mean, even if this was not there might be some of you who are like, I didn't need to go this deep, and that's fine. But are we okay with this definition and how we got here? Okay. And by no means am I saying this is the way to do this derivative. This is a way. There are many ways you could attack. All right. So now that I have all the right pieces and we're ready to go, how do I start thinking about the derivative? What is dy dx? If I'm going to think about it as these, in terms of these 4 functions, what rule am I having to use now? Product rule. So how does that work? So I need to take the derivative of a of b. Okay. So we got the product rule written out. Now we just really have 2 derivatives to do. What is the derivative of a of b of x going to be? times 2. Yep. Gotta take the derivative of the inside as well. This next one I can just rewrite. This next one I can just rewrite. And finally, all right, we done? Yep, gotta take the derivative of the inside. So 3x squared minus 1. Any questions on that? I could simplify, I'm not going to. I think leaving it in this form makes it quite a bit easier to see where everything came from. Which I think for this guy that had so many layers, I think it's important to see where everything came from. Any last questions on this example? Of course. All right, cool. I have one example left. We do not have time. Actually, I think I do have two. I am not going to go through them here. I'm going to post these slides in the next hour or so. I would encourage you to go in these slides, and even if you don't finish those last two derivatives, think about how you would attack them and think about how you would break them down. I think they're good practice. Otherwise, make sure I have your quizzes before you leave. I think that's it. I'll see you on Monday.